Thanks for joining me again today. Today we're going to hit some more things on the periodic table, specifically with valence electrons and oxidation numbers. Oxidation numbers probably a new term for you. Valence electrons may not be, but these are going to be some things we've discussed probably in previous episodes. However, these are going to be things that are going to be useful for us throughout the rest of the semester. So as we move forward, kind of our new content is thinking again, what are the pattern of electron structure on the periodic table? And then again, how can we use this pattern to predict the charge of an ion in an atom? So much of what we do in our chemistry class is about ions and bonding, and we can use these patterns to help us predict what's going to happen when bonding occurs when we have compounds. Not a lot of vocabulary today: valence electron, oxidation number, and ions. All right, so let's get to it. Back to valence electrons. Again, valence electrons, by definition, these are just our outer shell electrons, if you want to think of it with a Bohr model like we have in the picture on the right. So you can see in this one, there are 4 outer shell electrons. There's 6 total green ones. One of them's kind of covered up with my pen mechanism. But there's 4 on the outside shell. We would consider those to be the valence electrons. If we talk about SPDF electrons, the valence electrons are typically the S and P electrons. So in this picture over here, we could say that it has 4 outer shell electrons. We could be a little bit more specific and say which ones are S's and which ones are P's. This gets a little messier when we get to transition metals because they have these d orbitals, but we probably won't spend very much time there. So if we look at the model on the right again, we can describe it as having 4 valence electrons because it has the 4 electrons on the outside shell. So you can see right here, we've got 2, 3, and then one kind of behind the tool over here. And then more specifically, if we were talking about S's and P's, then there would be 2 S electrons. And again, the way it's drawn, we can't tell which one's which. And then there would be 2 P electrons. So the way this one ended, this would be 2s2, would also be 2p2. These 4 electrons would total up to be equal to what's in the outside valence shell that we have there. So 2 different ways to think about it. Regardless, we get 4 electrons in the outside. Now, when we get back to the periodic table, one of the things about the valence electrons is that elements in the same group are going to have the same number of valence electrons. And so the image on the right, these are all atoms from the alkali metals in group 1. And you can see starting with lithium, Li, sodium, potassium, all the way to francium, they are different. They get bigger and bigger and bigger. But if you look carefully, what we see is there is a similarity, because if you look at just the outside shell, you'll notice each of them is exactly the same in terms of its outside shell. It's just that the outside shell gets farther and farther away from the middle. And so they all have 1 valence electron. All right, so this is a helpful thing with the periodic table, because we can look at a group on the periodic table, and if we know the number of valence electrons in one of them, we should know the number of valence electrons in all of them. If we went back to the SPDF notation with these, we would say that they all would end in an S1. Lithium would end in 2s1, sodium would end in 3s1 because it's got 3 shells, potassium and 4s1, and so forth and so on. So we could say that their outside shell is exactly the same by picture, or we could say their outside shell is the same because they would all end in S1 if we were doing their electron configuration. So if we look on the periodic table, again, we should be able to use the periodic table to quickly know how many valence electrons each of our items would have without really having to do a whole lot. Again, this doesn't really work as well for the transition metals in the middle. However, if we just think of the tall columns across the top, I'll move this over a little bit. If we just have the tall columns at the top, you'll notice we've got 1, that's smaller, 2, we skip all of these. If we come over here, 3, 4, 5, 6, 7, and 8. The tall column basically tells us the number of valence electrons of any element in there. So the previous slide, I was showing examples of everything in group 1. So all of these would have 1 valence electron. All of these would have 2 valence electrons. The transition metals, again, a little bit more complicated. Some have 2, some have 3. Some may even have more than that. But then we get back to the other side. Again, these are all going to have 3. These are all going to have 4, 5, and so forth. Again, our exception is helium, because helium doesn't have 8 electrons. It's only got 2. But everything else in this last column would end up having 8. because the groupings are going to be based on the number of electrons they have, and the number of valence electrons is going to be consistent within a column. Again, helium is going to be our exception. Transition metals don't have quite that same pattern. We don't spend very much time with them, and so sometimes we have to look those up. So why is this useful to know? Well, again, it kind of relates to what we're going to eventually get into with chemical bonding. Elements rarely stay to themselves. They tend to bond with other atoms, where they end up forming compounds in order to form compounds. And there's a lot of rules that are involved with this, like which elements are going to be able to get together, and it often has to do with their electron structure. So if we know how many electrons an atom has on its outside shell, then it's oftentimes a lot easier to predict what's going to happen in terms of the bonding that would make. So the number of valence electrons is going to be an increasingly important thing as we move forward. The term oxidation number sounds kind of fancy, but it's related to the number of valence electrons. Basically, the oxidation number is because atoms would end up losing or gaining electrons if their outside shell is not full. In the picture we have right here, notice sodium has 1 valence electron, fluorine has 7. If you go through and count all of these that they have. All right. These elements like to have their outside shells full, and so oftentimes electrons may move from one to another, or they may be shared. And so what we end up with oftentimes is a resulting charge because electrons tend to go one place or another one. So in this example of sodium and fluorine, it's very likely that sodium would lose this electron because there's only one, and fluorine would actually maybe gain an electron because it's got an extra space for one. That oxidation number tells us the resulting charge. So if we look at something like sodium, its electrons are negative. What's going to happen with sodium? If it loses a negative, sodium is going to end up having a positive charge. Right? Fluorine, on the other hand, because it's gaining an electron, is going to end up having a negative charge. So if we lose electrons, we become positive. If we gain electrons, we become negative. And again, these are not things that we have to memorize because there's patterns going back on the periodic table. So if we think about how many electrons things have, that's going to relate to our oxidation number. All right, so again, elements in a group have the same number of valence electrons, so they're also going to have the same oxidation numbers. If we go back to this first group that we had before, remember they all have 1 valence electron. They tend to lose this electron, and when they lose that electron, they end up with a positive charge. Everything in group 2 has 2 electrons, and they still tend to lose those 2. And if you lose 2 negatives, you end up with a positive charge. And this trend happens once we get over here to the other side. Once we hit kind of in the middle, it's a little bit of a dividing line. We're not going to spend a whole lot of time with those right now. But as we get towards the right-hand side, the scenario changes a little bit because they end up not losing their electrons. They end up gaining them. So metals will tend to kind of want to empty out their shells, all right? So if they empty out their shells, they're going to lose their electrons. And again, when they lose their electrons, they end up getting these positive charges. On the other hand, once we move to the other side of the periodic table, nonmetals tend to have their valence shells more full than empty, right? So these have 5 electrons in them, these have 6, these have 7, and these have 8. So they're going to tend to gain their electrons, and when they tend to gain their electrons, they're going to end up getting a negative charge. Again, our exception with any of this is going to be our noble gases. They're at the very end, they're already full. All right. So in summary, move this out of the way if I can. All right, so again, our periodic table is related to the electron structures that we've got. If we look at the groups, they tend to they're going to share the same number of valence electrons. Because they share the same number of valence electrons, they're going to both also either gain the same number or they're going to lose the same number, which is what the oxidation number is. And that ends up being what the resulting charge of an ion is, just either positive or negative. So again, we can look on our periodic table, predict the number of valence electrons, predict the charge that it's going to have once it gains or loses.